Welcome to our Repetitorium today on the module transport processes. I hope all of you are fine and you are still healthy, hopefully, and not infected. I guess everybody recognizes that the infections come closer. Even me, I know at home is focused again because we have a COVID case in our family, unfortunately. Yeah, but we are still okay, and we hope that most of the examiners will stay healthy for the examens that are coming up now. This will be probably a very crucial time to have enough people who can examine and can take care of you in the examinations. Okay, before we start with the repetitorium, do you have any comment or question so far for the lecture or the situation or something like that? Some comments. By the way, maybe I can tell you that because I'm a senator as well of TOHH, and we have the Akademische Senatssitzung this afternoon. And I guess you know that we have strong discussions about these Freiversuch, and I just want to mention that we probably have a quite good solution for all of you that we don't will come into too much trouble. So please wait until I guess tomorrow we will get the official information about that. And we are sorry that the information comes short time, but even for us and even for the organization, for the presidium of TOHH, it's a very challenging situation. But we're working on a good solution. I hope that you will be satisfied afterwards with that.
I have a question. Can you upload the slides afterwards?
No, unfortunately not, because we never upload the slides for the repetitorium because we don't want that you feel safe with just these slides. Anna, this is the reason. Because this is just a brief summary of the lecture, but this does not mean that we will only ask for the slides that are in this repetitorium. Yeah, okay. So this is why we don't upload the slides. Sorry for that.
Okay, I understand.
Okay, any other questions or comments? Good. If not,
Professor Schlüter, you just muted yourself.
Thank you. I don't know how this works. Okay. Thank you. So let's go through the lecture, and we have a lot of slides, unfortunately, and it's a lot of stuff, but I guess it's a good opportunity for you to get an overview over the lectures. And if you have questions, then please keep the questions for after this lecture or for tomorrow, if we can discuss this again in the heat and mass transfer lecture. And of course, you can always reach me by email and can ask questions, and you can also address the questions to Sebastian or Daniel. Okay, so let's start. So you might remember at the beginning of the lecture, we started with this slide here, and maybe that at this point, this was not very clear for you why we use it. But I guess now at the end of the lecture, you have seen that we have these very strong similarities between momentum, energy, and mass transfer, and that it makes definitive sense to have it structured like this, to look on molecular transport in one dimension, steady state transport, convective transport across interfaces, in turbulent flows, in large systems, and to talk about multiphase systems, evaporation, condensation, and so on. So here we have very strong dependencies, and I hope that with this module you have a good overview of all these different transport processes now that are all related to each other. Yeah, we looked first in some typical equipment, for example, these straight tube heat exchanger, and of course it's helpful to know how such a straight heat tube exchanger is working, because this helps to understand a lot of the topics we discussed: boundary layers, convective flow, conduction. We talked about these energy pinch method for heat exchangers and so on. So I guess it's good to have this in mind, how a heat exchanger and a typical heat exchanger looks like. And this helps you to discuss maybe in your group about all the transport processes in such a heat exchanger. An important topic is, if we talk about heat exchange, the resistance against heat transfer. And if you think about fouling or different materials that are combined, then you need to know these steady state heat flux equation to calculate the heat flux through different layers of different conductivity. And this is something we very much like to ask you: how does a profile looks like in such a heat transfer process here, where the stronger gradients, where the slower gradients, and so on. So this is an important information. Yeah, I showed you this slide here about contact resistance, and this contact resistance might bring you some unsteady, not really unsteady, but some very different heat conductivities here in this area where we have bad contact between the metals or between the materials. But please don't mix this up with a Henry jump. Yeah, the Henry jump in mass transfer, this is really a jump. Yeah, an unsteady jump, because here we have the chemical potential that is different in two phases. This is a constant. This is a profile that can be calculated at each point if we know here's a situation in between. Yeah, so this is not a jump. This is a continuous slope, but a very, very different slope because of the contact problem here. Yeah, we talked about heat transfer in fins. You remember that we had these fins to increase the surface for heat transfer, and for that we derived the fin equation, and we derived as well the solutions for the fin equations. By the way, in general, you of course don't need to know all the equations that we use to derive such equations. It is only important to remember the final equation, and to have the opportunity to work with the final equation. For the exam, don't worry, we will give you these equations if it's necessary. But you should know how to calculate, for example, the heat transfer in the system. And as you know, it's a more or less a multiple choice examine, not really multiple choice, because we ask for diagrams, we ask for some explanations, and so on. It's not just to make it across. You have also answer questions, drawing diagrams, and so on. But you can imagine we will not have a big, complicated question, or you don't have to calculate really with this equation. It's more or less a question then what is taken into account here, and what does this ml value means, for example. And then you can explain this verbally in some sentences. You will not really do a calculation of the fin length. Or another opportunity might be in the exam to ask for the meaning of this diagram here. Yeah, you remember we have the diagram that takes into account here these dimensionless heat transfer value, and here we have these ml factor, these dimensionless parameter, and with increasing length, this is a dimensionless fin length, and with the increasing length we have an influence, of course, on the temperature. So the heat transfer performance itself increases, and the temperature difference here is the dimensionless temperature at the tip. So the temperature at the tip, of course, decreases, and if the fin is very long, then we have no change in the tip temperature anymore at a certain length. Yeah, and we already derived from this that beyond a length of 5 divided by m, here we have no heat transfer, almost no heat transfer anymore, depending on the length. So ml1 means this is a very stumpy fin, and the larger ml, the longer is the fin, and the less efficient is the fin. And if you're interested, you might remember that we distinguish between fin efficiency and fin effectivity. Yeah, you can look it up. Maybe it's good. I don't know if we asked for that, but fin efficiency and fin effectivity is quite, I guess, an interesting point. Okay, and here we have these dimension of length again. So then we talked about the convective heat transfer, and for convective heat and mass transfer, we repeated, I guess all of you know this already, but we repeated the overall balances, macroscopic balances, and of course every engineer should be able to write down a macroscopic balance. Here, for example, for the steer tank reactor, with the change of material in the system by time, and then the fluxes, the flux into the reactor, the flux out of the reactor, and some source or sinks, in this case, chemical reaction of this component A. And of course, you see this with this A, you have to do this balance, or you can do this balance for every component. Yeah, we talked about macroscopic balance equation. Also, the convective transfer, I guess, is clear. What is a little bit more challenging is turbulent transport. And here we introduced the analogy between the turbulent transport processes. And we saw that the turbulent momentum transfer here with these turbulent momentum transfer is in the same order of the turbulent heat transfer and the turbulent mass transfer. Now, this is because turbulence is nothing else than convection on a very tiny time and space scale. And therefore, if we have material that is transferred, then this carries heat and also mass. And therefore, we have this analogy, and this means we can estimate, for example, the turbulent increasement of heat transfer with the turbulent intensifying factor for momentum transfer, and also the mass transfer can be derived from that. And yeah, this was shown here. Here we have the turbulent momentum transfer. This is the black line here, the solid line, and the dashed line is the turbulent mass transfer. And you see the nice analogy here with these equations. So in the following, we talked with convective transfer about convective transfer in convective heat transfer in heat transfer networks. And here we worked on one example for a heat exchanger network. And you might remember we had this example here where we have different heat flows that have to be transferred, cooling systems and heating systems with a certain volume flow rate and certain temperature differences. And we found out that the most important point is here the enthalpy capacity for the systems. So how much heat can be transferred by a certain flow, and this can be covered with the enthalpy. And so we have here a certain enthalpy and here the certain temperature range. So the enthalpy, so the power that can be transferred in kilowatts, the power of heat that can be transferred in kilowatts, is one important parameter, and the other one is the temperature level that we have available. And the enthalpy difference, you can easily remember that if you think about exchange of heat between air and liquid. So if you would like to heat up air with a certain amount of liquid, then you need a lot of liquid to heat up the air. And you don't need so much liquid, because liquid has a much higher heat capacity than air. And the other way around, it's much easier. So of course it depends on the enthalpy, on the heat capacity of the fluids, and the enthalpy, how much heat can be transferred. And therefore we draw here the lines for different heat exchangers, for the cooling heat exchangers and for the heating heat exchangers. and then we shifted these two lines together until we get here a certain minimal distance, this pinch point of 10 degrees Celsius, because we say that round about rule of thumb 10 degrees are necessary for a sufficient heat transfer. And we can shift this here because the enthalpy is not an absolute value, it's always a difference between the inlet and the outlet flows. I recommend you to go once again through our example here to get a feeling how these energy pinch method for the heat exchanger networks work. Good. After that, we went from these convective heat transfer to the heat transfer at interfaces. And here we talked about first the boundary layers and how boundary layers are taken into account in the heat transfer equation. And you remember we simplified the temperature behavior, let's say the temperature increase in the boundary layer with the conductivity in the boundary layer and the boundary layer thickness, and this was simplified to the parameter alpha. So alpha is the heat transfer coefficient in watt per square meter Kelvin, and this can be used dimensionless with the Nusselt number. So we introduce here the Nusselt number at this point. I guess these are values that you of course know already from your bachelor studies, but repeated this here that everybody has the same basis of knowledge, and maybe with your knowledge now of fluid dynamics, you get deeper insights into these parameters. So here we have the very important alpha value and the Nusselt number, and of course this is something you need to have in mind if you would like to finish this module. Nobody will believe that you have heard a module about heat and mass transfer if you don't know the Nusselt number or the heat transfer coefficient. So please have this definitely in mind. And it's also very helpful. I very much recommend you to have the units in mind, because in many equations, or if you have to derive in the examined dimensionless numbers, it's extremely helpful to know the units of the parameters. So always, if you write down a parameter or write down a unit with a parameter, this is very important and extremely helpful. And believe me, it helps you in your professional career, because there will come a day and you will need the Nusselt number or the alpha value. And if you have still the units in mind, then this very, very strongly helps you to understand what's going on here. If you know this is a certain power per surface and temperature difference, that's nothing else what is given here, 1 per square meter Kelvin, then you have directly a feeling what this parameter means. Okay, so please try to keep this in mind. This is really, really, really helpful for your career as well. Good. If you talk about boundary layers, then you might remember we found out that the Prandtl number of the material is extremely important to describe how the boundary layers looks like. So here we see the boundary layer for momentum. So this is the fluid boundary layer here for momentum. So in other words, the velocity. This is how the velocity increases here with increasing distance from the surface. And here we have the temperature boundary layer. And the temperature boundary layer looks different than the boundary layer of the fluid. And it can look very similar if we have a Prandtl number of about 1, which means that the kinematic viscosity is in the same order than the heat transfer coefficient. Then we are in the order of 1. But if we have Prandtl numbers that are much larger than 1, then we have a dominance of the viscosity, and the heat transfer is less dominant. And this is the case that we have here. So here we have a very strong momentum transfer, but the heat transfer compared to this strong momentum transfer is very low, and therefore we have a very tiny boundary layer here for this situation. And the other way around, if we have a very high conductivity and a low viscosity, then the temperature profile reaches very deeply into the fluid dynamic bulk. And it's much larger than the boundary layer here. And this is important for you as engineers, because this means if you have this situation like with mercury or other liquid metals, then it does not matter if you decrease or increase the boundary layer thickness. So have different pumping volume flow rates and velocities here, because you have a very good heat transfer anyway. Here it makes definitely sense to decrease the boundary layer thickness, because otherwise you have here only heat transfer by these tiny boundary layer, and then here you need to have laminar transfer, so conduction as well, until you come into the bulk phase. Here it makes definitely sense here not to increase the volume flow rate. Yeah, and another must know is this diagram, because if we talk about the Nusselt number, that this is so important, then you should also have in mind, of course, a diagram how the Nusselt number depends on the most important parameter, which is, of course, the Reynolds number. Yeah, the Reynolds number is the number that influences the transfer processes, heat and mass transfer, and therefore you should have in mind how this looks like. And for heat transfer, it's like this diagram here. We have at the beginning a very horizontal behavior, because here we have almost conduction, and therefore the fluid flow does not have any strong influence. And with increasing Reynolds number, the convection gets more and more important, and therefore the convective heat transfer increases as well. And convective heat transfer means that the boundary layer thickness decreases. At the end, physically, with increasing Reynolds number, the boundary layer thickness decreases and enables stronger convective heat transfer. And an additional parameter is the Prandtl number here. So Prandtl number, you remember, was the viscosity divided by the heat transfer coefficient. And this means that we have here worst, so Prandtl number very slow means slow viscosity and high heat transfer performance, and this means we have also a high Nusselt number, and vice versa. Okay, so this is how the influence of the Prandtl number looks like here. So you can have in mind large Prandtl number, lower Nusselt number, small Prandtl number, higher Nusselt number. This is reciprocal. And don't forget, this is a double logarithmic scale that we see here. And you remember we have the same diagram for the Sherwood number, which is shows nicely the analogy between heat and mass transfer. Yeah, and if we want to calculate now the Nusselt number, then we can use empirical correlations. There are a lot of correlations in literature available here from the heat atlas, for example. And what you can see is that you will find mostly the same equation. For sure, if you look to that, then we see we have in general a dependency between Nusselt number and Reynolds Prandtl, and this is also taken into account here in this empirical equation. We have Reynolds and Prandtl, and then we have some exponents, Prandtl to the power of 1/3, for example, and Reynolds to the power of m, and a certain factor. And with that, we can model the Nusselt number dependency on the liquid velocity here and on the parameter of the liquid phase, the material properties. For example, if we have different viscosities of our liquids, then the different viscosity is here taken into account in the Reynolds number as well as in the Prandtl number. And by taking this into account, this equation should be valid as well for different viscosities.
I have a quick question, if that's possible.
Yeah.
Can you go a slide back to the Nusselt diagram?
Yeah.
Yeah. Did we not just say in the slide before that we have, when we have small Prandtl numbers, then it's not so effective to increase the Reynolds number to get a thinner boundary layer? But in the diagram, it looks quite good if we have low Prandtl numbers to increase the Reynolds number.
No, if we have small Prandtl numbers, like here, Prandtl goes to 0, then we have liquid metals, like liquid metals, and we have a very high heat transfer performance. And the boundary layer thickness goes very deep into the system. And so here we have already high Nusselt numbers. Yeah, that is what is mentioned here.
Okay.
Yeah, so here we have already high Nusselt numbers. If we look to the large Nusselt numbers here, like oils, then the Nusselt number is much smaller in general. Yeah, and therefore here it makes sense to increase the volume flow rate, because you see here it makes sense to go to higher Reynolds numbers. And here we have already large Nusselt numbers.
Okay. Thank you.
You're welcome. Good. And then we talked about mass transfer at interfaces. And for mass transfer at interfaces, we introduced especially this Henry jump. And you might remember it is possible to transfer mass against the concentration difference. This is totally different to the heat transfer due to the laws of thermodynamics. It's not possible to come from a lower temperature level to a higher temperature level. For mass transfer, it's possible. You can come from a lower concentration level to a higher concentration level. This is shown here. You see here we have a low concentration, and here a high concentration. And despite the fact the concentration is transferred, the mass is transferred in this direction. And this is possible due to the Henry jump. This is probably the most important difference between heat and mass transfer. That you have a jump, the first important difference, because this means the two materials, how they interact, is extremely important at the interface. And also that you can come from lower concentration, let's say potential, to higher potential, which is very, very uncommon. But potential is not the right word, because concentration might be different, but the chemical potential, by the way, is still higher on this side than on that side. Yeah, so from the chemical potential side of view, we have the right situation here. And this takes into account as well here the unsteady heat transfer. You see that with increasing time, the concentration here goes down, and here the concentration goes up. And important is that the Henry jump keeps constant. So independently of concentration, how this changes by mass transfer, the jump keeps constant. Good, and so we introduced as well the mass transfer coefficient in analogy to the heat transfer coefficient. Everything is very similar, and for the Nusselt number, we have now here the Sherwood number with the mass transfer coefficient, the characteristic length, and the diameter. The diffusion coefficient, of course. And these characteristic length, like in all dimensionless numbers, this is always a little bit critical, because if we talk about the plate, then you have a length of the plate, for example. If you have a cylinder, then this might be the diameter of the cylinder, or for a bubble, it's a diameter of a bubble. But what kind of L do you use if you have non-spherical or more complicated shaped bodies? Yeah, then it gets difficult. So this L is always a critical point. What is the characteristic length? So, and once again, the Sherwood number is proportional to the diffusion coefficient divided by the boundary layer thickness. If diffusion increases, mass transfer increases, and if the boundary layer thickness decreases, mass transfer increases as well. I guess this is physically easy to understand. And here we are with a second diagram that is analog to the diagram for the Nusselt number. Here we have the Sherwood number, and here we have the convection number. In this case, it's not Reynolds-Prandtl, it's Reynolds-Schmidt. So Reynolds, once again, for the velocity, and the Schmidt number that gives us a ratio between the viscous transfer and the diffusive transfer. In this case, it's nu divided by d, you might remember. So kinematic viscosity divided by the diffusion coefficient. And here we have the example from heat transfer. And even here, it's the same then with the Prandtl number. With the Schmidt number, if the Schmidt number goes down, then the Sherwood number goes up. And if the Schmidt number goes down, goes up here to Schmidt infinity, then we have lower mass transfer performances. And once again, this is always a nice question to you in the exam. How does a line here starts on the left-hand side? And of course, with very low Reynolds number here, we have only diffusion. And this means if we have only diffusion, then the diffusion is much more dominant than the convection. Therefore, the Reynolds number is not very important. And therefore, we start here with a horizontal line with a mean Sherwood number. And by the way, this is 2 here. It's nice if you can have this in mind that we have starting here with a 2. And then our usual equation looks like with a Nusselt number 2 plus, and then C multiplied by Reynolds to the power of something and Schmidt to the power of something. This is a usual equation to derive this, describe these lines. Good. We talked further on about free convection. And for the free convection, we showed you how to couple the momentum and energy transfer. So we have here the typical Navier-Stokes equation that describes the flow field. And additionally, so with the convective part and with the part for the viscous effects here. And additionally, we introduced here with a gravity and gravity that acts on the flow field by different temperatures. So the influence, this beta, was the expansion coefficient, thermal expansion coefficient, and the thermal expansion coefficient means how is the density changing with changing temperature. Yeah, so this is the influence of the changing density by changing temperature. And this means that if we have a cold, more heavy liquid, then this goes down, and hot, more lighter fluid goes upwards. This is why we have these free convection. And this can be modeled with the Grashof number here and the Prandtl number. So you see, usually we have Nusselt dependency of Reynolds and Prandtl, but now we have no forced convection. We have free convection here by gravity effects by different densities. And this is taken into account with the Grashof number. And you found this influence here once again with these expansion coefficient beta. And so this is a Grashof number dependency, and we can combine these two parameters here into the so-called Rayleigh number. Grashof multiplied by Prandtl gives us a Rayleigh number. So further on, we talked about unsteady heat transfer. You might remember the samurai sword, where the different temperature with the cooling down process enters changes the hardness of metal or steel. And so it's important to know how the temperature profile penetrates into a material in time. And this is what we have calculated here, and we derived for that the unsteady heat transfer equation. With some simplifications, we saw that the temperature in time is only dependent on the temperature coefficient here and the second deviation of the temperature profile in these three group directions. And with the thermal diffusivity here, Temperaturleitfähigkeit, we were able to to write this here with the Nabla operator. It's a little bit shorter. And now the question is, how can we solve this equation? And we saw that this is not very simple, because we need some assumptions here, and we need to use the similarity of these profiles. But some of the students have already seen this fluid dynamic lecture for the unsteady momentum transfer, and therefore we derived this E function for that. But before we did that, we talked about influences on this unsteady heat transfer. And this unsteady heat transfer depends on how strong the heat is convected at the outside of our body here, and how the heat transfer works inside of the body. And we saw that this unsteady heat transfer performance can be described with a PO number, which takes into account the convection at the outside and the conduction in the inside, so with alpha and lambda. And this means that we have a very good conduction in the insides, and we have no profile in the inside, and only at the outside we have these gradients. And the opposite is if we have very strong convective heat transfer and a bad conduction inside of the material, then we have these strong gradients of the temperature in the material and almost constant temperature at the outside. And these boundary conditions helps us to get solutions for the unsteady heat transfer equation. And because this is so important, we derived a dimensionless number to describe this. And this is a BO number. Oh, sorry. This is a BO number. The BO number that brings these convective and conductive heat transfer into a certain relation. So if the BO number is very small, then we have almost conduction inside the material. If the BO number is very large, it's very large, and we have very good transfer at the outside, and we have the resistance inside of the body. Yeah, and with these simplifications, we were able to derive these to solve the unsteady heat transfer equation, and this is what comes out with the error function. We get this equation here, and even in this case, don't worry, you don't have to derive the equation, of course. It's just I guess helpful for you to know how we have derived it and what is necessary to derive it. It's important that you know what's going on here, how the error function, so let's say an artificial function, is used to describe the profile, that you need this dimensionless temperature difference, and that of course time plays here a big role, and the position of the profile in the system, so the X position, as well as the thermal diffusivity here. And you see once again the strong analogy between momentum transfer, heat transfer, and mass transfer. It's always the same to describe the same structure of the equation to describe the unsteady process. Okay, brief 2 minutes, and then we go further on and talk about the mass transfer at fluid interfaces. We discussed here some different models to describe mass transfer at interfaces. And this is the film theory and the penetration theory. These are the two most important ones, that assuming if we have a certain concentration in the gas phase and the liquid phase, that we have here in between a linear concentration behavior, concentration slope. But don't forget, in the middle we still have our Henry jump. Please never forget to write and draw this jump here. And this is the film theory that assumes that we have two films of a certain thickness. And another model is taken into account that we have some dynamic exchanges at the interface. So a fluid element is transported to the interface, and then we have a certain contact time where the fluid is loaded with a component here, with a gaseous component in that case, and then it's leaving the interface after a certain time. So whereas here you have to model the boundary layer thickness, so here we have the delta L that have to be modeled, or the delta gas, depending on if you want to calculate the beta gas or beta L liquid. And here the time has to be modeled. So this is the time, the contact time of our fluid element at the interface. So the time has to be modeled. Here the thickness has to be modeled of the interface. And of course, it depends a little bit on how steady your process is. If you have a steady rising gas bubble, then you can use both. If you have very dynamic situations like turbulence, then probably the lower model is more suitable. Yeah, here we have the equations for the theories. Once again, the field theory, but I already mentioned that. Here you have some typical values, and here's the penetration theory once again, but I already mentioned the equation. Yeah, then we made some experts into heat transfer and the design of recuperators. So we talked a little bit about design and scale up, you remember, and we calculated these recuperators here as one example for heat transfer and design of these kind of fins. And then we talked about evaporation, and for evaporation we use this Nikoyama's experiment to explain what's going on. And yeah, I recommend you to remember this experiment because, of course, it very nicely shows all the dependencies that are important to understand evaporation and what's going on during evaporation with the heat transfer performance. And what you hopefully remember is that if you increase the current here, then the temperature of this wire increases. And we can measure with the current directly the temperature, because we know the dependency between resistance and temperature. So we know the power that is transferred here into the wire, and with this power we can calculate the heat that is transferred, and we can measure the temperature, the oversaturated temperature of the system. And if we do that, then we see that we have different dependency here of the heat flux and the wall superheat, so the temperature of the wire minus the saturation temperature of the liquid. And we see that first we have almost natural convection, then first vapor bubbles appear, so this is this region of isolated bubbles, and if we increase the temperature further, then more and more vapor bubbles appear, and we get strong turbulence vapor bubbling here, so this is a regime of jets and columns, of bubble jets and bubble columns. And then we have here these very, very important point that you please never forget as engineers. This is this heat peak, where we have no opportunity to increase the heat flux anymore. And the reason is that at this point we get a dry surface. Yeah, this is a heat peak, or the dry out point, and this is very, very important, because if you have a dry surface and you have no opportunity anymore to transfer the heat convective by the liquid phase, it's only radiation that takes place here. So we have a very strong and dangerous drop of the heat transfer performance. And as you can see, this drop is here in the double logarithmic diagram. This means from this point we go from 20-degree superheat suddenly to 200-degree superheat, and suddenly very easy we can also come to much higher temperatures if the heat flux is constant, like in a nuclear power plant, or if you have a chemical reaction or something like this. So very important, please keep in this safe area here and don't go too close to this peak heat point here. The same is of course true for heat exchanger pipes, for cooling pipes, for example, cooling pipes for cooling processes. And here we have once again the same situation. First we have convection, then we go over the saturation temperature. First vapor bubbles appear, and more vapor appears here. We have a more almost constant temperature, because evaporation is taking all the heat for changing from the liquid to the gaseous to the steam phase. And then at this point we have the dry out point, where we get the dry surface, and then suddenly the temperature jumps up to a much higher temperature, and this brings us into trouble here, because we have only heat transfer by radiation. Some dust, maybe some not dust, mist, sorry, some mist here that is transfers some heat, but it's almost radiation that comes into play here if the temperature increases further. Yeah, it would be very good to be able to draw such a diagram here or this one and to recall these different parameters. This would be a nice question for the examen, that we write down this diagram and you have to show what point is what happens at the different points. Yeah, and last but not least, we talked about heat radiation, and to talk about radiation, you first need to know what is the black body that absorbs all radiation, all visible radiation that comes into the body, and that transfer all the radiation that enters the body into heat to make radiative heat measurable. It's necessary to transfer all radiation that enters the body into heat, and this can be done by this black body. So all the rays are trapped here, and this trap, the only possibility for the energy to exit this body is via heat, and therefore we will get a certain temperature here in this Hohlraum, and this temperature directly depends on the energy. So here we have the emissivity as the energy, and depends directly on this temperature if we have a black body. And the dependency is given here with the so-called Stefan Boltzmann constant. Stefan Boltzmann's law says that this energy here is the Boltzmann constant multiplied by temperature to the power of 4. And as we talked about that, we looked on this Leslie's cube, and this Leslie's cube showed us that, of course, not every body is a black body, because depending on the surface, we might have more or less strong radiation of heat to the environment. Here, for example, we see that the heat from this hand here is reflected at this polished surface, whereas here, if we have these hot surfaces, there's no strong difference in the temperature. So the effectiveness in emitting energy depends on the surface coating as well. So this is why the black body approximation is so important. Yeah, but as mentioned, usually our real bodies are not black, but they have some certain opportunities to reflect or to transmit radiation, and therefore we have to switch to this gray body approximation, and for that we introduce this epsilon factor here to the emissive power. This is the emittance. So the emission power is reduced by the emittance, because we have not really a black body that traps all the radiation, but some radiation is already still reflected, and this brings us to the gray body approximation. Yeah, and then finally we talked about few factors to be able to calculate the heat exchange between different surfaces, and by radiation. Yeah, it's just for the radiation, and of course here Stefan Boltzmann's law plays a big role still. The temperature difference multiplied by the constant, and then we have this view factor that takes into account how strong radiation exits and enters on the opposite surface. And this is another nice point where we can ask you in the examen to find the right view factor for certain problems. Don't worry, we will not ask you for such equations here, but just to see if you have understood what's going on with this view factor. Yeah, then we talked a little bit about the design of solar collectors, but I guess we don't have to go into detail here. And also we saw that there are analogies between electricity and the resistance in electricity and the resistance in radiation for heat transfer. But even that will not be addressed in the examen. Don't worry, this is just for you to remember. Okay, so sorry for talking too much. This was a very fast and brief summary of the lecture heat and mass transfer. But we have a second one. And this is a multi-phase flow lecture. I give you maybe 1 minute to relax a little bit, and then we continue with this. Yeah, actually, I guess you have seen in the last semester that it does not make really much sense to separate between heat and mass transfer and multiphase flows, because very often it's directly related to each other. And even in the problem that you have to solve during your professional career, you will see that this is very, very often very close connected. Anyway, because this has been 2 lectures, I separated this into these 2 repetitoriums. But in the examen, you will have both topics mixed. But I guess it's not very challenging for you because it belongs to each other anyway. So I start with this very boring slide that you probably have already in mind. This shows you what kind of interface combinations you might have in the multi-phase flows. Of course, all these are just 2 phase flows with 2 different phases. Of course, in multi-phase flows, we can have, in industrial applications, usually we have much more phases than just 2. So here are some typical apparatuses. On the left-hand side, we see droplet swarms. So here is liquid is feeded here. So this is obviously a kind of droplet tower. Gas is coming from below, so this may be a washing process, a gas washing process here, where some contaminants like sulfur is washed out of the exhaust gas here. The clean gas is exiting the system here. In the middle, we have a typical bubble column situation where gas is fed into a liquid phase. Bubbles are rising upwards. This is here a countercurrent bubble column because liquid is fed here and exits the reactor below the aeration plate here. And the third very typical application for multiphase flows is the extraction column that you can see here on the right-hand side. And here we have the situation that we have a liquid-liquid system. So we have liquid droplets that are fed into a liquid phase. These liquid here has a lower density, which means that the droplets are rising. And during this rising process, the liquid's carrying some components that are solved in these liquid here. This process is very often used if you have sensitive products, for example, flavors or something like that, or drugs that have to be carefully extracted from a liquid with low concentration. So liquid dispersed, gas continuous, liquid continuous, gas dispersed, and here we have dispersed liquid in a continuous liquid phase. And what you can already see, what is the most important point here always is the interface, because the interface dominates the heat and mass transfer processes. So we have to think about interfaces. And this is why we started in this lecture to study a little bit more in detail what interfaces means and how interfaces are influenced by certain properties, for example, here by the surface tension. So this is a droplet that lays on the surface, and this shows how we can calculate the contact angle here with different surface tensions. And also the capillary law has once again been introduced, where we know that the liquid in a capillary rises a certain height in dependency of this contact angle. The gravity here plays, of course, a role, the diameter of the capillary, the density, and of course here this contact angle once again. So in other words, the more tiny the capillary is, the smaller the diameter, the higher rises the level. By the way, this is something I very much would like to recommend you for your studies, for your master's studies anyway, in every subject. Please try to always to understand the equations by changing parameters and think about what's going on there, because this gives you a feeling how what is the physics behind these equations, and then it's much easier for you to keep these equations in mind. And sometimes it shows you the errors in the slides or in the equations. Okay, we talked about bubble formation, and for the bubble formation process, this capillary pressure here was very important. So we talked about the Laplace pressure that can be calculated here with the radius of a bubble. So in this case, it might be not a spherical. We can have different radii here in this case. So this is the surface tension, and this is the pressure difference between the pressure inside of the bubble and the outside. And you see that more tiny the radius is, the more increases the pressure. And because this is 1 divided by r, this means the pressure increases dramatically if the radius gets very tiny. In other words, you need a very high pressure first to start to create a bubble, because first the radius is very small. So this is why we first need a big peak of pressure here. So about 70, 80 millibars. And then if the bubble is already formed and the radius increases, then it drops, and then we have some fluctuations here. And then the pressure might be lower than 0, interestingly, if the bubble buoyancy is so large that the bubble tends to disappear here. So this is a bubble formation process, and you see that, of course, the buoyancy plays a big role, calculated here with delta P and the bubble diameter, the cross-section, and the surface tension that tries to keep the bubble back. Here we have sigma multiplied by PD. This is the force that tries to keep the bubble back. And so with this force balance, we can try to estimate the bubble size. We talked about trickle films, hydrodynamics in trickle films, and for that we made another force balance, a liquid film, and this liquid film is here on a pipe wall running down the pipe wall, and we introduces the thickness of this liquid film delta, and we saw that we have a certain velocity profile in the film that influences the film thickness. And so with thickness and profile, we can estimate the volume flow rate that runs down the film. And we can do a force balance here, once again, on this film. And this means that the shear force that acts here on the wall, this is a shear force, needs to be in equilibrium with the gravitational force that acts here on the film. So, and here we have the gravitation. So this is a gravitation. Here we have the shear force, and both needs to be in equilibrium. And if we do that, then we can derive the equations for the film. And so I already mentioned the dimensionless. So the film thickness depends on the circumference of the pipe and the volume flow rate and the boundary layer thickness. So this can be here estimated, and then we see that the thickness depends on the Reynolds number. So the Reynolds number gets, the smaller gets this dimensionless film thickness. It's a dimensionless. The thickness itself, of course, gets larger, but because we divide here by volume flow rate and circumference, it goes, it gets smaller, the dimensionless one. Yeah, we see that we can influence the film thickness here with the Reynolds number, and we have a certain point where we switch from this slope of the Reynolds number to another, and this is because we have here the laminar film situation, and at Reynolds of 400, it switched to a wavy and more turbulent film. From the films that appears here directly on the particles, we switched to the overall trickle bed reactor and tried to understand the fluid dynamics in the trickle bed reactor. And we saw that we have here in trickle bed reactor different regimes that have to be distinguished. So, and the most efficient flow regimes are here these trickle film and pulse flow situation. Spray flow and bubble flow is usually not this effective. In the bubble flow, the whole trickle bed is filled with liquid. In the spray flow, we have only a little bit liquid as spray and almost gas. And from that, you can directly derive these dependencies here. What is used for the characterization of the flow pattern is the superficial gas velocity on the left-hand side, the left axis, and here the superficial liquid velocity on the lower axis. And spray flow, of course, as mentioned, very high superficial gas velocity, low superficial liquid velocity, and vice versa, high liquid velocity and less gas means we come to bubbles. So you know bubble and spray flow, and then you can see where pulse trickle flow is located. Of course, this depends on geometry and of your column and also fluid properties and operation pressure, but this is a general diagram to explain the flow properties. By the way, once again, double logarithmic, yeah, so you should remember this. Yeah, for the design of the trickle bed reactor, or let's say the design of all reactors, pressure drop is always a very hot topic. And so we looked on pressure drop correlations. Yeah, this was probably for you, even for me, the most disappointing point of this lecture, that always if it gets interesting, we have to switch to just empirical equations because it's too difficult and much too complex to take into account all properties and operation conditions in analytical solutions. Nature is complicated, unfortunately, and therefore I had to show you these correlations, these empirical correlations from some examples. And in the meanwhile, you have done a very, very good job with your PBL. And from this PBL, you probably have seen that there are lots of different correlations around, and it's extremely difficult to decide which one is the most reliable. And I hope that I was able a little bit to show you in this lecture how to decide which correlation should be used and which is probably more reliable and which not, and how to use these correlations. Yeah, one of them was this friction factor equation here that gives you the friction factor for trickle bed reactors with the pressure drop per length of the trickle bed, and here the diameter of the column, superficial gas velocity, and important is here this friction factor takes into account the as most important parameters, the Reynolds number of the fluid and the Weber number. Weber number, you should remember that the Weber number takes into account surface tension. Yeah, if you see Weber, then you should directly think, oh, there is surface tension. It plays here an important role because the Weber number is the dimension of surface tension. And yeah, for sure, this plays a role with surface tension because you can imagine if you have a trickle flow and you have a very low surface tension, you have probably totally different flow structure compared to a high surface tension, because at a low surface tension, bubbles will be much smaller, or droplets, and with high surface tension, the droplets and bubbles will be larger, and this of course influences pressure drop. So this is why this factor here depends on the Locard-Martinelli parameter, taking into account the ratio of gas and liquid superficial velocities and surface tension with the Weber number, and of course Reynolds number, the volume flow rate. And with this, the friction factor is modeled. Yeah. This was a friction factor for trickle bed reactors. One equation, one example of an equation. Yeah, we talked about flow structures in pipe flows as well. So trickle bed film flows and pipe flows, film flows and trickle bed reactors was one application. pipe flows and traveler reactors, the other applications. So we start to talk about flow situations, fluid dynamics in pipes. And there was this important diagram where we talked first about flow structures, these multi-phase pipe flows. And we see superficial gas velocity once again on the left-hand side, and the superficial liquid velocity on the lower axis here. Once again, double logarithmic. And like before, we can go to the extreme points to see what's going on. So, of course, if we have a very low liquid velocity and a very, very high gas velocity, then we will have more or less mist here in the system, mist or fog or whatever you would like to call this. So this is an annular flow. Yeah, so we might have a very tiny layer of liquid in at the wall of a pipe, but we have more or less gas and tiny droplets. So this is a mist flow. The opposite side, we have very high liquid velocities. So the system is, let's say, filled with liquid and only a little bit gas. Then we have the bubbly flow. And so please go through this diagram in this way to find the right flow structure. And this, of course, is another example for the examen that can be nicely asked. To fill out these different sections, like this is our test exam. So for the pipe flow, we did once again first an analytical solution. We derived an analytical solution for the momentum transfer. So we made a momentum balance for the pipe flow, and at the end we found the continuum equation, momentum equation, and energy equation for this pipe flows with the simplicities that we have these unknowns. We need to know the velocities of gas and liquid phase, vapor fraction, and the pressure drop. This has been the important parameters that need to be known, and or at the end that need to be modeled to describe the pipe flow reliably. And therefore, first of all, once again, the fraction, so how much vapor or how much gas hold up do we have in the system? Once again, an empirical correlation. Yeah, and once again, yeah, please don't try to learn this equations here. This makes no sense because in your career you will look them up anyway. And it's more important that you see what's inside these equations and how are they structured. Yeah, for sure, the vapor fraction here plays a role, and also some coefficients. And then the fruit number here is an important parameter that takes into account the gravity. So these are more important points that you understand a little bit how the equations have derived and how they are structured. Okay, so bubble formation. I already mentioned that before. We talked about bubble and droplet formation processes, particle formation. Here we have the droplets below and the bubbles here, and we see it's a very similar process. The only difference is that here we have a separation of bubbles in the gas jetting regime, and here we have more disintegration of jets for liquid drops. And we see that we have an analogy at the point of Weber2, so surface tension once again is the important parameter. We have a transition from the single particle formation to these more, let's say, chain of bubbles and droplets. And this shows how this works for gassing problems. So we have the Weber number here again. So this is once again the critical Weber number of 2, where the surface tension plays a role. And here we have the bubble diameter. And we see here we have this quasi-static bubble formation. And at the point we are larger than 2. So we switch from these periodic formation here to the more regime transition to the more chains of bubbles and drops. Then we have more influence of momentum, and this brings us to two bubble on droplet sizes, here in this case bubble sizes. We have larger bubbles as well as smaller so-called secondary bubbles that are breaking up here by momentum. So the large ones are still stable, and we get additionally tiny bubbles that are appearing by breakup. So primary and secondary bubbles, and with this diagram here we can estimate bubble size. Yeah, talking about the formation, we derived and looked on the force balance at a bubble with the buoyancy force and the surface tension force, viscous force, and the momentum force. And by using an equilibrium of all these forces, we can derive a particle diameter. And yeah, this is calculable with a diagram and a derivation as well. I don't want to go into detail here, but of course it would be a nice question to ask you what kind of forces do you know that are act on a bubble during a bubble formation process. But you don't need to write this in detail here, but just the forces might be interesting to ask. And the same is true for the force balance at a rising bubble. This is a very nice question, by the way, that is very often asked as well in the PhD defenses, because it's a nice fundamental question and not very difficult to answer. You just need to know the force balance at a rising particle. So what kind of forces do you have? You have the gravitational force. Yeah, this is calculated with the volume of the bubble and the, of course, particle density. And you have the buoyancy force that is calculated with the volume of the liquid, so liquid density, bubble volume that is depleted by the bubble. And then we have additionally the drag force, is rho divided by 2, multiplied by the velocity to the power of 2, multiplied by the cross-section here, A, and multiplied by a drag coefficient. This is a conventional drag force equation that you probably know from many, many other problems. Yeah, and that's all. And if you bring these three forces into equilibrium, then you end up with Newton's law of motion here that can be derived from this very simple force balance. Please try this by yourself. This is good training, and it's very nice to do these calculations. You need to have in mind this is a relative velocity. It's the relative velocity of the bubble here, and this relative velocity can be different from an absolute velocity that is calculated with the surrounding fluid. So if the fluid is moving upwards, then the absolute velocity is this relative velocity plus the liquid velocity. So please have this velocities in mind. So here it's given once again, the relative velocity is the velocity of the bubble, and then we have the fluid velocity from the Euler view and the particle velocity, the absolute particle velocity in Euler view. Talking about bubble velocities, we need to remember the circulation inside of fluid particles, because we have here Newton's law of motion with the drag coefficient, and the drag coefficient is the only unknown parameter in this case here. And this drag coefficient has to be modeled, and we know this drag coefficient from many equations for solids, where we have a no-slip condition here at the surface of the particle. But for liquids, it's more challenging, because if we have a liquid fluid particle, so a liquid or gas, then we have an internal circulation due to the shear forces here at the wall. And this means that this internal circulation reduces the drag coefficient. The particle appears smaller than it is due to the internal circulation, because the no-slip point is shifted into the middle of the particle here. So therefore, this is one reason why bubbles has a lower drag coefficient than solid particles, and why the velocity of bubbles is usually higher than the velocity of droplets. Of course, the density difference is in that case more important, but the friction factor here is the drag coefficient can play a role as well. And this is why the drag line or the dimensionless velocities for bubbles looks a little bit strange. So we have here a solid particle first, then internal circulation comes into play, and at this important point here, and this is at bubble diameters in air in water, for example, at a range of 4 to 7 millimeters, then suddenly the shape of the bubble shifts to such an idle shape, and this means that due to the bad drag, we have a much higher drag coefficient and therefore a decreasing velocity. And this is somehow strange. The same size of the bubble increases, and despite the fact the size increases, the bubble gets slower because the shape is changing. And here we have a formless shape, which means that we get with increasing volume and increasing velocity. So you should have this diagram in mind. It's something that we very much like to ask you, how the behavior is of gas bubbles. And please don't forget, this is a double logarithmic scale again here in this diagram. And you see this diagram is made dimensionless by using the fluid number here, Kf, that takes into account all important fluid properties like density, viscosity, and surface tension. And with this dimensionless parameters here, we can use this diagram for many different material systems. Yeah, talking about bubble shape, we can talk about the Edwards number that shows us how the shape of the different bubbles are changing. Here we will not go into too much detail. This is just an opportunity to characterize the shape of the bubbles. And if we have not only one bubble, but many bubbles, like usually in industrial applications, we have to take into account that we have a countercurrent flow in between the bubbles, or the particles. It's the same for solid particles. So if particles are sedimenting down or rising up, then they are depleting water or liquid here, and the liquid has to go somewhere, and due to the continuation of mass, the liquid has to flow through these particles, and this means that we have let's say, artificial higher velocity in between the particles. Not artificial, we really have a higher velocity. And this is taken into account by these laws, here, for example, from Richardson and Zaki, that says the higher the hold up, the lower the swarm velocity of the particles. Last week we had the question, sorry, I have not already added that here. I this for the next semester. That this is a single particle velocity here, and this is a swarm particle velocity. There are more complicated equations, but yeah, I don't want to emphasize on that right now. Yeah, talking about columns and real two-phase flow structures, we have to mention once again the homogeneous and the heterogeneous flow regimes. You might remember that we have much higher surface tension, much higher interfacial areas in the homogeneous regime because the bubbles are smaller, but mixing is better in the heterogeneous regime because we have bubbles with different rising velocities. And the transition is very important here, transition point, because heat and mass transfer performance strongly, and mixing performance strongly changes in these two regimes. And to find out where the transition happens, we can use such diagram. We can just look up the gas hold up in dependency of the superficial gas velocity, and we will see that at a certain point here, the gas hold up suddenly drops, and this is the point where we have the transition from homogeneous to heterogeneous regime. Even that is quite strange. We have more gas that we feed into the column, but despite the fact we feed more gas into the column, the gas hold up drops. And the reason is that bigger bubbles are formed that are much faster rising, and therefore the gas hold up drops. Despite the fact we feed more gas into the column. Good, we talked about mass transfer. We already had this slide. here and saw how mass transfer works. We had this in the heat and mass transfer lecture as well. Therefore, I guess I can fast go over these slides because we just repeat that Henry jump, concentration difference, and this is the equation to calculate at the end the heat transfer, the mass transfer performance with the KLA value, the saturation concentration in the bulk phase here, and and the concentration in the bulk phase. And from this simple equation, you already see where the problem lies, because the saturation concentration can be looked up in textbooks, for example. This is a physical parameter. But what is about the concentration in the bulk phase here? Because this concentration will depend on mixing, on back mixing, on chemical reactions, on biochemical reaction, and whatever. So this one is difficult to estimate. And please remember Henry's jump. Henry's jump is the ratio of saturation concentrations in the gas and the liquid phase. And to derive from these KLA values, the total mass that is transferred, we can calculate this with the reactor volume. And then we can calculate this with KLA value. We need to know the specific surface area here. For the specific surface area, we can use this equation that is derived from a geometrical assumptions, and it means that we have 6 multiplied by the gas hole up divided by the solder diameter. This gives us a specific surface area here. Yeah, this was a balance of for mass transfer to derive the equation for the overall mass balance. This can also be used for the static mass transfer measurements to derive the KLA value. So the volume flow that goes into the system multiplied by the concentration difference in minus out is the same than the concentration, the mass that is transferred from all the bubbles. So in other words, we have to use the concentration difference, saturation concentration minus concentration in the liquid multiplied by the reactor volume. This is the most precise opportunity to calculate the KLA value. But the problem, you need to know A, and this is not easy to derive. So we talked about the mass transfer performance concerning the mean share number, but we already saw this diagram. I can skip this, I guess, but we talked additionally about unsteady mass transfer. And for the unsteady mass transfer, the time comes into play. That is made here dimensionless by the Fourier number. The Fourier number is the dimensionless time, and we see that with increasing time or increasing Fourier number, the mass transfer performance decreases. And this is because the concentration difference decreases, because if more and more mass goes out of a bubble or a droplet, concentration difference decreases, and this means that the transfer performance decreases as well. And it's nice to look here on the extreme points at very low Fourier numbers, very short times, we have more molecular transfer, and here at very large times, the mass transfer is almost completed, and therefore we have no influence here and there, here only a little bit, but further here, there's no influence of the convection anymore, of the Reynolds number. That has a strong influence here in between. So with increasing Reynolds number, we can increase the Sherwood number, but at very small, short times and long times, not anymore. Yeah, then we switched over to reactive mass transfer, and we saw that we have a certain, let's say, a reaction front where two components are reacting. Here in this case, we have a concentration of B and a concentration of A. And at this point here, where the concentration of both is 0, we have the reaction and another product, for example, C appears. And this reaction front is penetrating in time and space into the system. So here we have the entrance number, 10 to the minus power of -4, -3, -2. So in other words, here a film runs down a surface, and with increasing distance from the entrance and increasing time, concentration front penetrates deeper into the film. Yeah, please try to intended to remember how this penetration runs and what is the influence of the Dampf-Kühler number that takes into account the reaction constant. The higher the Dampf-Kühler number, the higher the part of the reaction and the higher the mass transfer performance and the enhancement factor that gives us a ratio between non-reactive mass transfer, reactive mass transfer to non-reactive mass transfer. Here you can see that with the reaction, we can enhance the mass transfer by the factor of 10, which is a lot here, because it means a 10 times smaller reactor, right? And the enhancement has been shown here once again, non-reactive mass transfer, reactive mass transfer to non-reactive mass transfer. This can also be described with the Hatta number, which means that if the Hatta number is between 0.3 and 3, then we have a medium fast reaction. Smaller than 0.3 is a slow reaction, larger than 3 fast reaction. Good, and then last but not least, we talked a little bit about balance, about the population balances. So we saw that the mass, the interfacial mass, the interfacial area is very important. So how can we calculate that? And we saw that there are different mechanisms that can be taken into account in these population balance modeling in kernels like coalescence and bouncing. And we saw some physical points, how these coalescence or bouncing, where it depends from, and how also breakup depends on that vortices are hitting a bubble or a droplet, and this energy from the impact of a vortice might bring us to separation of two particles. This is modeled in kernels. Okay, 2 minutes before 11:15. So this was a very fast jump through these lectures. I stay here a little bit if you have questions, but I hope it was not too much for you, and I hope it was more helpful to see once again the dependencies between the different points and what might be worth to keep in mind, even for the exam and beyond, of course, for your professional career. And yeah, we see us, some of you tomorrow once again for discussion, and for whom I will not see tomorrow again, I would like directly to wish you all the best and a very successful exam. And to all of you, I would like to thank you once again for your interest and the very nice discussions that during this semester. I very, very much regret that I've not seen us more often in presence. Yeah, but we are all suffering from this situation, I guess, and we made the best of it. And you did a very, very good job, by the way. And I very much hope that we will see this as well in the exam. Yeah, thank you so much. Keep healthy for the exam. And I guess we will give you some more additional instructions and tips and assistance for the exams before the exams takes place. Okay, do you have any questions left or comments? Okay, some question or comment in the chat. Do you upload these slides? I know, unfortunately, I will not upload the slides because I mentioned at the beginning that I don't want to feel you safe with these slides. No, because of course this was not. There might be some questions in the exam that I have not addressed here in these slides. Yeah, so this is why we never uploading this, and we also not record this lecture because of this reason. Because you should have a look on the whole script, and you should try to find your own, let's say, summary of the script. And this was just a service for you here today to give you an overview. But of course, you can always ask me. You can always ask our PDL students, and also Sebastian and also Daniel. And by the way, I very much would like to thank them. I would very much like to thank our students for assisting in the PBL. I guess they did an extremely good job, and thank you so much, and also to Daniel and to Sebastian, of course, for assisting this lecture.
Also, maybe I would like to mention like one little thing before there are any misunderstandings. What Mr. Stüter said in the very beginning, or within the first 10 minutes, there won't be any calculations in the exam. So because the last exam was a take-home exam, obviously you understand that we might change some tasks or some parts of the exam to the previous ones. So there might be let's say simple equations to solve, maybe like kind of similar to the previous one. And of course, if it's getting too complicated, we give you the basic equation. But don't think that you don't need to calculate anything. So there will be some basic equations coming up in the exam. But you anyways should know them if you have followed the entire lecture. So no worry about that.
Yeah, thank you, Sebastian, for this clarification. Very important. And yeah, for example, we will not give you the Nusselt number, for example, or the Reynolds number, or the Sherwood number. Yeah, that's something you need to definitely need to know. But for example, the equation for the unsteady mass transfer, probably that will be given. Yeah, so that's how it works. Good. Any other question or comment?
I have a question. You just said in the first lecture of multi-phase flow something about interface and surface, but we always talk about interface during the lecture afterwards. But you said there in the first lecture that the interface is a phase between two liquid phases.
Yeah, thank you. Ms. Menzel, you're probably right. It might be that we mixed up this sometimes in the lecture. The correct term, you are totally right, is surface for gas-liquid and interface for liquid-liquid interfaces. That's right. I apologize if I mix this up sometimes.
Okay.
Any further points?
Then maybe I can continue. I have another question. What is the difference between the bubble and the droplet? Is it just that the bubble is the droplet is liquid and the bubble is gaseous phase, or?
Yes, that's a difference. Bubble is always gaseous dispersed phase, and a droplet is a liquid dispersed phase.
Okay.
Mm-hmm. But good to ask, because indeed this is very often mixed up. But that's a correct definition. Okay, if there's not any other question or comment right now, or we are quite tired, I am, due to talking 1.5 hours. And yeah, then please take your time for tomorrow, maybe for further questions. And if you have any other points, you can always address us and ask us, and we can do another Zoom meeting or whatever you want if you have further questions.
Maybe I can.
Thank you.
Sorry, maybe I can continue because I have some more questions.
Of course.
Do we have a Henry drum between the liquid and liquid interface? Normally not, or?
Yes.
Yes, as well.
Yes, for mass transfer, you have always a Henry jump. You even between liquid and solid surface, what is difficult to understand, but even there you have a liquid, you have a Henry jump. For this is, for example, important for membrane processes. Might have to do membrane. So Henry jumps always appearing if you have an interface and mass transfer across interface.
Okay, that wasn't clear for me just yet. Okay, thank you. And another question, when we had the model the boundary layer theories,
Mhm.
we had 4, and normally we had 1 model parameter, but you didn't mention it for the boundary layer theory.
Model parameter for boundary layer theory.
Yeah, for example, for the penetration, it was the residence time, and for the surface renewal theory, it was the frequency.
Yeah,
I
here,
think,
you mean this one? You mean the film theory, right?
yes, and there I talked about the boundary layer theory. We had 4 of the series. But it isn't mentioned in this slides, it's mentioned in the...
Okay. The boundary layer theory, I don't remember, I must say.
It was in the lecture 5, sorry, lecture 5 of heat and mass transfer.
Lecture 5, let's see. I can try to find it. In the heat and mass transfer lecture or the multiphase flows?
No, the heat and mass transfer lectures, page 34 to 47.
Yeah. 1 second. So here we go. 47.
34, yes, here, these are the slides from the different theories. And there you always mentioned a model parameter.
Yeah.
Here, for example, the residence time for the frequency, but for the boundary layer theory, you didn't mention.
Yeah, okay. Yeah, you mean here is. Okay. Yeah, for the boundary layer theory, this is the theory that needs most information, because you need to know here the profile of the concentration inside the boundary layer. And therefore, I have not, I did not go here to in more details, because it's quite complicated. You really need to solve the equations to get the real slope here. Or you can use even these the error function to describe this. Yeah, there's another opportunity to, if you have a non-steady transfer. But it's quite complicated here. This is why I did not went into detail. And this is also not very common. This is not very often used. So the penetration theory and the two-film theory are the most important ones.
Okay.
But it's a good point. I have to add this here. What is the model parameter? That there is no model parameter, because the profile is directly solved here inside.
Okay. And we had also in the heat and mass transfer lectures, we also had some scale-up criteria. Is it normal that we use the Reynolds number and the Newton number, or do we use other dimensionless numbers as well?
The Reynolds and Newton number is usually used on the Newton number for stirred tank reactors. Yeah, this is a classical dimensionless number for scaling up stirred tank reactors.
And then it's always like that we take them constant, or that we assume them constant to make the scale up.
Yes, exactly. Yeah, this is the idea behind the dimensionless numbers, that you try to keep them constant. But as I mentioned, unfortunately, it's not possible to keep all dimensionless numbers constant. So then it's you have to decide which one is more important and less important, and this is sometimes not easy to explain. But you should try to keep them constant. Or let's say as constant as possible.
Yes. Okay. Then another question to the Fruit number. The Fruit number, I just, as you said, just took all the units of the single values inside the Fruit number, and it didn't get dimensionless. It was in in the lecture 9 of heat and mass transfer.
Let's see, that's a little bit strange. Of course, it has to be dimensionless.
Maybe I made a mistake.
Heat and mass transfer lecture 9.
Mhm.
9. So let's see. Can you tell me the slide, please?
Yes, it's slide 12.
12. Mixing and mass transfer? Now here. Yes, I have it on 30. I don't know why.
Because N is the Storer frequency, right?
N is the Storer frequency. It's to the power of 3 here.
Right, and the
To the
Storer
power of 2.
There's
10 to the power of 2.
That's right. It's to the power of 2. There's a mistake in the slide. Very good.
Okay.
Thank you so much. Very good. I correct that.
Okay.
You're right.
Okay.
Perfect. Thank you. Of course, this is what I mentioned in the repetitorium. If you know the units, this is very helpful sometimes. It shows you the errors in the slides. Here we have this case. Yeah. Thank you.
Mm-hmm.
I'm sorry for that. I have to correct that.
No problem. And I have some, I didn't understand page 14 and 15 because, for example, here we said with increasing Storer frequency, we have an increasing root number. And I thought that if you increase the Storer frequency, you come from the homogeneous to the heterogeneous bubble regime and not the other way around.
Let's see. So, by the way, I have to correct this here as well. So, you mean if we increase the Storer frequency like this on
Yes.
this one? So we increase the Storer frequency, and this means by increasing the Storer frequency, we come to more breakup here. Yeah, and this brings us a better distribution of the bubbles, and this brings us here to a more or less homogeneous bubble regime because the bubbles get smaller and better distributed, and by that we come to the homogeneous regime. And here we have the heterogeneous because we have strong convection.
Okay.
Strong free convection by the or buoyancy-driven flows, let's say. Yeah. Yeah.
But I thought with more energy you have stronger turbulence as well.
Yeah, that's right. That's not easy to understand, Ms. Menzel. This is something that we have found out and have published, and that was not known in the community 2 years ago. It's a little bit complicated. Of course, the Storer makes more turbulence. Yeah, so if you increase the velocity, but what is much more dominant here is the large-scale flow structure that is introduced by the bubbles, because they are rising very fast and they are introducing here a big loop, and this brings much more turbulence into the system and unsteady flows compared to what the Storer is doing. Yeah, and this is that, of course, you still have here strong liquid turbulence, no question, but the bubbles are rising much more homogeneously here, and therefore the whole situation in the system is more homogeneous. It's not laminar, it's far away from laminar, of course. Yeah, but it's a strong turbulent system, but it's homogeneous because these bubbles are rising homogeneously.
Okay. Now I understand that. And in the next slide, you said something about loading and flooding. Can you explain this once more?
Yeah, this means loading means that all the bubbles that are fed here, all the gas that is fed, can break up at the Storer. So the Storer is able to break up all the bubbles and to distribute all the bubbles in the system. And this is loading because all the bubbles that are entering the reactor are breaking up and are introduced here into the whole two-phase flow situation in the reactor. And flooding means that so much gas is entering the system that the stirrer is not able anymore to disintegrate all bubbles, only a few one. And therefore, a lot of gas can pass the stirrer without being disturbed, without a breakup. And this is a flooding regime. So the stirrer is so-called flooded.
Okay. I thought I was confused because flooding normally is for the liquid phase. In my head, I thought it's the liquid phase. And
you're right. Yeah, you're right. No, in this case, it's to the gaseous phase. Yes. Mm-hmm.
Okay. And then when we measure the KLA value, you said something about measuring without consumption of dissolved gas and measuring with consumption of dissolved gas.
Yeah.
Is it the difference between if there takes place a reaction and not?
Yes, exactly. Yeah, a sink of dissolved gas is a reaction. Yes, chemical reaction or biochemical reaction.
Okay. And there were also two graphics. Maybe can you explain them for me?
Yeah.
It's also in the lecture line, page 38, and 38.
38. You mean this one?
I think it's afterwards. Yes.
This one.
This one. Mm-hmm.
Yeah, this one is a method for KLA measurements. And what you're doing here is this is in the case that you have a certain consumer of oxygen here in this case, like a chemical reaction or chemical reaction. It's very often used for, you have a consumption of dissolved gas. Very often this method is used for bioprocesses. If you would like to know the KLA value for a bioprocess, yeah, you have a bubble column where you have biomass inside, and the biomass uses oxygen for the transfer process, for the conversion process. So let's say the bacteria are breathing oxygen. Yeah, so here we feed oxygen into the system, and as long as we have a constant oxygen concentration, everything is fine. If you stop the oxygen concentration, then the concentration decreases. Yeah, this is what happens in reality. And here we mimic this situation by adding nitrogen. So we have a constant oxygen concentration, we are adding nitrogen, and the nitrogen strips out the oxygen. And therefore the oxygen concentration decreases. Yeah. And then at this point, we stop aeration by nitrogen, and we add aeration by air, and then the oxygen concentration increases again. So oxygen concentration increases again. And yeah, these are the equation how these looks like, and therefore you see here we have the natural logarithm, which means that if we use a logarithmic scale here, this gets to a linear line, and then we can use the slope of the linear line to get the KLA value.
Okay. And on the next page, it's quite similar, the graphic.
Yeah.
So it's only the difference with, yes, I don't know where's the difference. It's quite the same, right?
Yeah, this is quite the same one. Yes, that's right. But here we're looking at, this is just another. Here we use the OTR.
The oxygen uptake rate and oxygen transfer rate.
Yeah, this is oxygen transfer rate. Yes, this is another expression that is used in biochemistry usually, but it's the same.
Mm-hmm.
And here, by the way, we have this what I mentioned before with the bacteria that are or chemical reaction. This is a oxygen uptake rate. Yeah, so much oxygen to the bacteria's let's say breath. Yeah, this is the oxygen uptake rate, and this is how the concentration decreases.
Okay. With the experiment of Mukayama, I have a question also, because why doesn't water just boil there on a normal boiling temperature, but always a few degrees up from that? I think if I boil water at home, I think it's always at 100 degrees, but maybe it's always like this, that it's a few degrees up, or is it only in this experiment?
No, I guess it's indeed a little bit higher, because you need some energy to overcome these bubble formation, these gas bubble or vapor bubble formation point.
Okay.
Yeah, and therefore, maybe you can think about, I talked about these stones that you add to the liquid to avoid that you have this higher temperature than 100 degree. So I guess you always need a little bit higher temperature than just 100 degree.
Okay.
I guess if the if the water is cooking, I guess then it's fine, because you have enough, let's say, nucleation points in the water that the transfer can happen. So that means then you will have indeed these 100 degree. But until you get the first bubble, that vapor bubble that appears, I think you need to overcome 100 degree a little bit.
Okay. And here in the Repetitorium, you said something about what do you call it? The film layer thickness, and something about the Reynolds number over 400. Then it's getting turbulent. Is it for a plate?
Yes, this is for the plate.
Because normally in the pipe it's 2,300 or something like that.
Yeah, that's right. This is for the plate. Yeah, by the way, this is indeed anyway an important point. Yeah, I mentioned that as well in the Repetitorium. It always depends on these characteristic lengths, and if you have different geometries, like a pipe, like a ball, sphere, plate, then you will have different characteristic lengths. Of course, you have to be very careful with that. And then, of course, these critical numbers as well change. Yeah, these 2,400 is only valid for pipes, for pipe Reynolds numbers.
Yeah.
Battery fully charged.
And in one slide of multiphase flow, you mentioned that we always have a homogeneous distribution of gaseous, liquid phase, and of particles. But for example, in the trickle bed, normally the continuous phase is the gas phase. Why should it be distributed?
Can you please tell which slide you
It's in the lecture 9, page 16.
Multiphase flow?
Multiphase flow, yes.
Trickle bed reactors, slide 16.
Yeah, we talked about local hydrodynamics.
Yeah. So this one?
Yes. And here you said homogeneous distribution of gaseous and liquid phase, and of course of particles. In the particles, I see it, and in this case, the liquid phase should be distributed as well, but the gaseous phase is continuous. Why should it be distributed?
Homogeneous distribution of gases and liquid. Yeah, it might be a little bit misleading here. With homogeneous distributed, it's mentioned that the flow through the packing should be homogeneously. Yeah, because even if the full system is full gas, you feed the gas here at the top. Yeah, and if this is not homogeneously distributed, then this means you might have a dead zone here of gas where no gas is exchanged, and gas is only running here at this side of the column, for example. Yeah, and that would be, of course, very bad.
Yes, I understand.
Yeah, that is what is mentioned with that. But maybe, yeah, it's a little bit misleading. Not just distribution. It could be maybe, I don't know, homogeneous feed or something like that of gaseous and liquid phase. Maybe this is more clear.
Yes. Okay, I understand. Here in the Repetitorium, you had the graphic where the dimensionless velocity is over the dimensionless particle diameter. And you said something about the fluid number.
Yeah. Let's see. Which slide was that?
I don't know which slide because it doesn't set on the the bottom.
Where was it? At the beginning, probably. No.
I think it was more in the end. It's in multiphase flows.
What was the question?
The fluid number. You said something about the fluid number there. Now, here it.
Yeah. Yeah.
Here. Yes. This is it. And I don't know here because I thought that it depends the fluid number. If you have different fluid numbers, then the shape changed. Ellipsoid bubbles. I change at different particle diameters.
Yeah.
Is cut C the same as the fluid number?
Oh, sorry. Yeah, you're right. This is also misleading. You're right. I'm sorry for that. That's true. It's the same one.
Oh, okay, good.
Fluid number and Kc is the same one. Kc is here in this diagram. I guess C stands for continuous phase.
Okay.
It's the fluid phase, of course. Sorry for that.
Okay, I think that was all.
Okay, perfect.
Thank you.
No, thank you. This is very, very helpful, and it helps me to improve the lecture, of course. Thank you so much. And if you have further questions, then please collect them. And tomorrow we have another opportunity to talk about these points. And as I mentioned, also whenever you have questions, please come to us and ask.
Yes, I will do that.
Perfect. Okay. Good. Then thank you all very much, and I wish you a nice afternoon, and hope to see you tomorrow again.
Thank you.
Bye.
Thank you.
Bye.
Bye-bye.
Bye.